There is a groundbreaking development in Africa. The rift is several miles long, and some believe it is a sign the continent is splitting in two.
Did you know that in some parts of Utah, the ground can crack for miles and sink more than a foot in a year because of how water is used? Small shifts underground may sound harmless, but they can open narrow gaps that widen over time and damage roads, pipes, or fields. Many don't realize that pumping more water than what returns can make fine layers of soil press together, causing uneven sinking and splits at the surface. Today we explore earth splitting in Utah. Utah has places where the ground cracks or settles over time because of what lies under the surface. These cracks may appear slowly or in a shorter span, and they can follow straight lines across fields, roads, or open land. Some cracks form as water is drawn out of underground layers faster than it returns. When water is removed, fine layers of silt or clay lose support and press closer together, causing the surface to sink unevenly and sometimes split. In parts of Utah, people have seen long, narrow cracks stretching for hundreds or even thousands of feet. At first they may be small, but over time they can grow wider or deeper. They often align with the way sediments beneath have shifted or compressed. Over weeks or years, tiny shifts underground lead to visible breaks at the surface. A narrow opening of an inch or two can become wide enough to pose a risk for vehicles or people. In some valleys, cracks extend to the water table and carry water deep underground, which can erode sides and make the opening larger when rain or floodwater flows in. Farmers, planners, and residents have noted such fissures and learned that they link to the balance of groundwater use and recharge. In southern Utah valleys, experts have watched how water use affects land. When wells pump water for homes, farms, or towns, the level of groundwater goes down. As water levels fall, clay or silt layers shrink in thickness. That shrinkage lowers the ground surface gradually. If pumping continues, the effect grows. In one valley, water levels dropped by tens of feet over years, and surveys showed land sinking by more than a foot across large areas. After some time, cracks appeared, running in straight lines across farmland and roads. These openings sometimes cut through fields or under pavement. Where a crack crosses a road, it can break the surface, making repairs needed. When it crosses utility lines or pipes, it can interrupt service or make gravity-based flow, like sewer lines, fail. In one housing area, a fissure crossed lots and damaged streets and sewer pipes, so gravity flow was lost. Local groups then had to plan repairs and find ways to slow water use so cracks would not grow further. Residents often first notice small shifts in yards or fields, such as tiny depressions, cracks in soil, or changes in drainage patterns after rain. Fences may tilt or show gaps near the ground. Shallow wells may run dry more often or yield less water. Springs may stop flowing. When people see these signs, they may report them to local geologists or water officials. Early reports help experts measure water levels and ground elevation. Monitoring those trends can prompt steps to slow water use before larger cracks open. In some rural areas, a crack may open under a tractor wheel or trap livestock if it goes unseen in tall grass. In towns near the edge of growing zones, a fissure might undermine a driveway or break a sidewalk. Noticing small changes early helps avoid costly damage later. In valleys where growth has been rapid, demand for water rises. New homes or farms often rely on wells. Without planning for water limits, pumping can exceed what the aquifer can supply over time. As more wells tap into water, water levels drop faster and deep layers compact more quickly. That leads to more uneven settling. When parts of the ground sink more than others, tension can cause a crack. Mapping where water levels have fallen and where land has sunk shows where cracks are likely to open. Experts measure water levels in observation wells over years, then compare with land surveys or satellite data that detect small vertical changes. When those data point to a pattern of uneven sinking, planners can identify high-risk zones. Climate factors play a role. Dry years and hotter weather increase water demand and lower natural recharge. Less snow in mountains means less spring runoff. Rivers and streams carry less water, so people rely more on wells. In a dry season, farmers may pump extra to keep crops alive. In towns, water use rises for lawns or pools. As pumping speeds up, groundwater levels drop further and fine layers compress more. Even if pumping slows later, deep layers may continue to adjust, causing further slow sinking over years. That means damage can continue even after water use is cut back. Knowing this, water managers watch weather forecasts and plan for seasons when surface water may not meet needs. They may store extra water in wet years to use later or direct surplus into aquifer recharge when possible. Monitoring uses tools like GPS or satellite radar to track ground elevation changes. These tools detect tiny shifts of millimeters per year. When combined with well-level data, experts see how pumping links to land movement. Mapping existing cracks shows how they follow patterns of subsidence. Models then predict where tension may build next. This helps avoid placing new roads or buildings across zones likely to split. For existing infrastructure, flexible designs such as joints in pipes or bridges that span small gaps can reduce damage if movement occurs. In many cases, avoiding building on high-risk land is simpler than fixing damage later. Water use planning aims to balance needs with the long-term health of aquifers. Farmers can adopt more efficient irrigation methods that use less water. Urban users can fix leaks, use low-flow fixtures, and choose landscaping suited to arid climate. Some areas reuse treated wastewater for irrigation or industrial needs, reducing pressure on fresh groundwater. Where geology allows, water managers may inject water back into aquifers when surplus is available, though such projects need careful study. Slowing the decline of water levels reduces the chance of new cracks. Full recovery of deep layers may take years or decades after pumping slows, so keeping water levels from dropping too far is vital. Policies vary by basin. In Utah, some basins have set limits on new well permits when signs of overuse appear. Water rights laws and local rules may cap total pumping or require permits for new wells in vulnerable areas. Users may share data on water levels and land changes to keep trust. In some places, water rights transfers or water banking allow users to shift water use as conditions change. When data show land sinking or cracks forming, groups may agree to reduce use or find new supply sources. Sometimes transporting surface water to a basin helps, but moving water long distances has cost and energy demands. Decisions weigh the cost of new supply versus risks of damage from cracks and land shifts. Natural cracks in rock appear too, but they differ in cause and scale. In places like Canyonlands or Zion, deep fissures formed over millions of years by movement in bedrock and erosion. Rock layers shift along faults or joints under tension, then wind and water wear the surfaces. Visitors may see narrow canyons or deep crevices carved in sandstone. These natural features show long-term changes of the land, but pose hazards for hikers if they fall in. They are not linked to water pumping but to tectonic forces and erosion over geologic time. Understanding both natural and human-related cracks helps people see how ground can shift at different timescales. When a new crack appears, reporting it helps experts assess risk. A small crack in remote land may not cause harm immediately, but if development or roads extend there, The crack could intersect utilities or paths. In farming areas, equipment could break if it passes over a hidden fissure. Fences or irrigation pipes might break along a crack. Ranchers may fence off areas with visible cracks. Wildlife or livestock might fall or get stuck. In towns, a crack under a driveway or yard can lead to costly repair. Marking fissures on maps helps avoid building across them and keeps people safe. Repairing damage can be costly. Roads may need patching, utility lines may need rerouting or flexible connections, and foundations may require extra support. Insurance policies may not cover damage from ground movement linked to aquifer decline, so homeowners and developers need to know risks before building. Engineering fixes address symptoms locally, but the core solution lies in managing groundwater use. If water levels drop too far and deep layers compact, the aquifer loses storage capacity permanently. That means less water can be stored, raising risk of shortages. Once compaction happens, even if water levels rebound partly, land may continue sinking slowly. That makes avoiding overuse from the start a priority. Community engagement and clear information help. Sharing simple data on water levels and land shifts builds awareness. Showing examples of cracks and damaged roads makes the issue real for non-experts. Town meetings, online maps, or reports from geological surveys can explain why limiting water use matters. Education programs in schools or outreach by water districts encourage habits like fixing leaks or choosing water-wise plants. When people see how pumping links to land changes, they understand the need for conservation and planning. Research continues to refine knowledge of how sediments compress and cracks form. Lab tests on samples show how different layers respond to pressure changes. Field data track actual behavior under changing water levels. Models simulate how pumping patterns affect subsidence and where cracks may open. Remote sensing tools track ground changes precisely. Partnerships among universities, surveys, and agencies help share knowledge. That lets water managers set realistic water budgets and guide development away from high-risk zones. Ecosystems may change when cracks appear. In farmland, fissures can alter irrigation flow, making fields harder to water evenly. In wetlands or riparian areas, cracks may drain water deeper, drying habitats that depend on shallow water. In deserts, cracks can collect rainwater and form small pools, which may help some plants but can also erode soils and harm others. In natural areas, openings may let invasive plants or animals move deeper underground or alter surface water patterns. Understanding these effects helps land managers balance human water use with ecosystem health. In areas where few people use groundwater, declines happen slowly and cracks may not appear for a long time. In fast-growing zones, heavy pumping speeds decline and triggers cracks sooner. Urban growth in desert basins raises hard questions about how much water is available long-term. Surface water imports may help but cost more. Capturing runoff in wet years to recharge aquifers may work if geology allows. Conservation measures, pricing that reflects scarcity, or incentives for efficient use can reduce demand. Coordination among users is key because one person's pump can affect neighbors by lowering water levels region-wide. Signs often appear before full cracks open: wells running dry, lower yields in dry seasons, springs failing, small depressions or soil cracks, shifts in fences or pavements. Monitoring these signs prompts action. When locals report changes, experts measure water levels and land shifts. Early warnings let users slow pumping before major fissures form. This saves costs and avoids hazards. Mapping tools like satellite radar detect tiny shifts over wide areas. GPS can track vertical changes of millimeters per year. Combined with well data, these tools show subsidence trends. When sinking accelerates, risk of new cracks rises. Maps of existing fissures show how they align with patterns of sinking. Models can point to areas where stress will build next. Sharing maps with planners guides where to build or not build. If a zone shows uneven sinking, policies may limit new wells or guide building designs that can handle slight movement. Legal and policy frameworks steer water use. In Utah, water rights law and local rules manage groundwater. When signs of overuse appear, authorities may limit new well permits or set total pumping caps. Users may share data on water levels and land shifts to keep trust. Water rights transfers or banking allow seasonal adjustments. When maps show sinking or cracks, stakeholders may agree on steps to reduce pumping or find new supply. Moving surface water into a basin can help but has cost and energy trade-offs. Communities weigh cost of new supply against risk of damage from cracks and sinking. Engineering may try to repair small cracks, filling them in roads or adding support under pipes. Foundations in new buildings may span cracks or use flexible joints for utilities. But large engineering fixes for widespread subsidence are rare, since the problem is tied to aquifer change. Recharge projects may inject water back when possible, slowing water level drop but requiring careful design. Such fixes address local symptoms, while main action remains managing pumping. Once deep layers compact, storage capacity drops and full recovery is unlikely. So prevention is vital. Climate outlook affects planning. Models suggest hotter temperatures and more drought spells in the region. Less mountain snow means lower river flows. More reliance on wells raises risk of subsidence. Water managers plan for lower supplies by storing water in good years, reusing treated water, or adjusting cropping and landscaping choices. Policies that balance growth with sustainable use ease pressure on aquifers and help avoid more land damage. Communication is vital for communities. Clear updates on water levels and land shifts build support for limits or conservation measures. Showing real examples of cracks and damage helps people grasp why action matters. Simple language and concrete examples work best. Outreach via meetings, websites, or reports from geological surveys helps non-experts understand links between pumping and cracks. When residents learn why reducing water use or changing habits matters, cooperation grows. In farming areas, efficient irrigation tools like drip systems or soil moisture sensors use less water. Urban users fix leaks, install low-flow fixtures, and choose plants suited to the dry climate. Reusing treated water for irrigation or industry reduces fresh groundwater demand. When surplus water is available in wet years, some places inject it back into aquifers to slow level drops. These actions help keep water levels higher longer and reduce the chance that fine layers compress too much and cause cracks. Experts study past water level records and land surveys to see long-term trends. In some valleys, records going back many decades show steady declines as pumping exceeded recharge. Over time, fine layers compact under pressure and land sinks. When sinking is uneven, cracks open. By comparing basins, experts see which have thick clay layers that compact more or low recharge that hinders recovery. That guides where to set tighter water limits or seek new supplies. Natural cracks in rock remain as a reminder that land shifts over time. In public lands, deep fissures carved in rock formed over millions of years through movement in bedrock and erosion. While they pose hazards for hikers, they differ from cracks linked to water pumping. Natural cracks follow faults or joints in solid rock, while pumping-related cracks form in soft sediments above aquifers. Knowing the difference helps people understand that the ground shifts from both long-term geologic forces and human actions. When cracks form, land managers and planners mark their location so future development avoids them. Reports from residents help update maps. Early mapping can steer roads, pipelines, or buildings away from high-risk zones. In cases where infrastructure must cross a zone, designers use flexible connections or bridges that can span small gaps. Yet such measures work locally. Preventing more cracks depends on managing water use. If pumping is cut too late, deep compaction may continue for years, so acting early is key. Ecosystem impacts include changes in water flow in fields or natural areas. Cracks can carry rain or floodwater deep, draining wetlands or riparian zones that rely on shallow water. In deserts, cracks may collect water and create small pools, affecting plant growth or eroding soils. Wildlife that depends on shallow water may face stress. Understanding these impacts helps balance human water use with ecosystem needs. Insurance for damage from ground movement is complex because standard policies may not cover such losses. Homeowners in areas known for subsidence must know risks before building. Developers may need special designs or avoid certain land. Communities may share data and plan conservatively. The cost of limiting growth or finding new water sources must be weighed against potential repair costs and hazards later. Research continues on how sediments respond under changing water levels. Lab tests, field measurements, and models show how layers compress and where cracks may open. Remote sensing tracks ground changes precisely. This guides water budgets, planning, and policy to avoid major damage. Over time, some basins may not fully recover because deep layers compact permanently when water levels drop too far. That reduces aquifer storage capacity and raises risk of future shortages. Knowing this, water managers aim to avoid pushing water levels beyond safe limits. They set realistic water budgets and plan for alternative supplies or stronger conservation if needed. Thanks for watching. If this topic caught your interest, please like and subscribe. Share your thoughts or questions in the comments, and tell us if you've seen signs of ground changes where you live. Your feedback helps guide future videos. Stay curious and safe as we learn more about how our actions affect the land around us.